So welcome to the 48th lecture of this course. I'll continue with this center tap full wave rectifier with you, and today I'll discuss the efficiency of this. Efficiency neta of this center tap full wave rectifier. I have already discussed the center tap full wave rectifier with you with the circuit diagram. This is a circuit diagram, the corresponding waveforms, and the working of this with you. Two diodes, of course it is equal to this much, and then IDC is equal to this much and IRMS is equal to this much, twice Im by pi and RMS value of this output current. I found the RMS value and the DC value of this output current of a center tap full wave rectifier. So now as far as the efficiency is concerned, I have already defined the efficiency denoted by neta. It is equal to the DC power delivered to load. DC power delivered to load. Of course, if I assume that load is RL, it is a ratio of DC power delivered to the load to the AC input power. AC input power, or I can say that in general I say that I represent this DC power by PDC. This neta is equal to PDC upon AC power, the ratio of DC power to AC power. Now let's find out the value of this PDC. This DC power is across this load. I am interested the power across this load resistance RL here, and the current flowing here, of course I'll find it if I apply a ammeter here, DC wattmeter here between this point and this point. I am interested in this, so current I assume as a DC current, so it will be IDC into RL, IDC square into RL. It will be equal to I DC square into RL. Now in the previous lecture I discussed with you, it is IDC square into RL, that IDC, since what is the value of IDC we derived, the value of IDC, since IDC for a center tap full wave rectifier, if you remember, it is equal to IDC is equal to twice Im by pi. So since IDC is equal to twice Im by pi, I substitute this IDC square is equal to this much, and of course if I find the value of PAC, I am interested in this PDC and PAC, it will be equal to, for AC always remember that we use RMS value along with RF and RL, I RMS square into RF plus RL. P is equal to I square R. Simply IDC into IDC square into RL and IRMS square into RF plus RL. And also we derived that the value of IRMS for a center tap full wave rectifier, for the output wave of center tap full wave rectifier, is equal to, since we know that IRMS, RMS value of the output current, RMS value of the pulsating DC that you obtain, the RMS value, it is equal to Im upon root 2. We derived this IRMS is equal to Im upon root 2 in the previous lecture. So finally I can say that this neta, therefore the value of neta, which is equal to PDC upon PAC, will be equal to IDC square into RL upon PAC is IRMS whole square into RF plus RL. Now I substitute the value of IDC and IRMS as 2 Im by pi and Im upon root 2. So I can say that the value of this neta is equal to, I substitute the value of this, twice Im by pi. So it will be twice Im by pi whole square, value of this, into RL. upon I RMS is Im upon root 2. So it will be Im upon root 2 whole square into Rf plus Rl. I hope that this simple mathematics is clear to you. Now, this Im square will cancel. 2 to the 4 to the 8. So it will be 8 upon pi square. This implies that value of neta will be equal to 8 upon pi square into RL upon Rf plus RL. This is in general the formula for the efficiency of a center tap full wave rectifier. This is the formula. If you remember that what we derived for half wave rectifier, the formula for half wave rectifier, the efficiency of half wave rectifier which we derived, efficiency for half wave rectifier, neta for half wave rectifier, we derived that this is equal to 4 upon pi square into RL load resistance upon the sum of forward resistance Rf plus RL. And if you compare these two, you just observe it is 4 here, rest quantities are same, it is 4 here and it is 8 here. So efficiency of a center tap full wave rectifier is double the efficiency of a half wave rectifier. So this is one of the advantage. It is required to have the maximum efficiency. Now let's find out the neta maximum also. So I can say that when will we have neta maximum? Let's make a corollary of this. That is, I can say neta will be equal to neta maximum when the diode is ideal one. It will be for the ideal diode. So for ideal diode, this implies that value of Rf tends to 0. For ideal diode, if I assume that you are using these diodes here, the diodes which are using in the circuit, if they are ideal one, if these diodes are ideal one, that is they are offering 0 resistance. Although practically it will have some resistance. Just for the sake of an argument, I assume that suppose this is an ideal diode having Rf is equal to 0. It means this quantity is equal to 0. This Rf, if this tends to 0, RL and RL will cancel. So it will have, you can say that the value of neta maximum value of neta will be equal to 8 upon pi square, and that is approximately equal to 81.2%. Approximately equal to, this is approximately equal to 81%, I can say. You just check it out, multiply this by 100. This is not exact, but it is approximately more than 80%. In the previous case it was approximately 40%, here it is more than 80%, double of it. So this is the efficiency of a center tap full wave rectifier. So what we have done so far, some parameters: what is the DC value of the output current, DC value of output voltage, DC value of RMS value of output current, and RMS value of output voltage, and of course what is the DC power, AC power, and the efficiency of a center tap full wave rectifier. I'll discuss a very small numerical based on it, based on a center tap full wave rectifier or a center tap rectifier. So let's take a numerical problem, for example. This is a problem here. The problem says that suppose you have the circuit here. Okay, I'll draw. You have a circuit here. An AC signal is applied in the primary of this. I'll just give you the value of this, and it is having two diodes here, diode D1 and diode D2, and it has been center tapped and a load resistance. Center tap, don't forget to ground this point. So these are the two diodes, and this is the load resistance RL. Now suppose I assume, I say that the input applied here, the input applied here is the input applied at this point is, suppose I say it is equal to 200 sine 50 pi t omega t. This is what it is. And suppose I say that each diode is having a forward resistance of this much, 50 ohm. This is also having a forward resistance of 50 ohm. This is given to you. What I am writing in with blue pen is given to you. And suppose this load resistance, I assume that this load resistance is of 1 kilo ohm. This is a problem. It is equal to this much, and it is a, suppose I say it is a 5:1 center tap transformer here. So in other words, what I mean to say that a signal of this much value is applied to the primary of a 5:1 center tap transformer, which is used in a full wave rectifier. Simple as it is. And if the load resistance is 1 kilo ohm, each diode having a forward resistance of 50 ohm, then determine, I say, then determine what you have to find. Problem for the given figure, for the given circuit, I say find, determine I say that first part, I am IDC IRMS. These all things points you have to find out. Second point, I say find the value of PDC. I have just discussed what do you mean by PDC. Then third point, find the value of PAC. And fourth, find the value of efficiency. That's all. These parameters you have to find out. Now look at this very first thing, what is given to you. It is given in the problem that you have this, I assume that, suppose I say that this is RF. Now I name this voltage, I say that suppose this voltage I name this as Vs. This is Vs given to you. This is turns ratio, I assume this as N1 and this as N2. This diode resistance, I say that this is RF, and this load resistance I assume this as RL. That is what is given to me. Just I am writing what is given to me is the supply voltage Vs. The supply voltage Vs. Vs is given to me 200 sine 50 pi t. That is, if I say what is the maximum, or okay, let's write out few more things. N1 upon N2. N1 is to N2. Turns ratio of this transformer is 5:1. Forward resistance of the diode RF is 50 ohm, and load resistance RL is 1 kilo. It's not, yes, it is 1 kilo ohm. 1 kilo ohm, or I can say this is equal to 1000 ohm. For simplicity, I generally take it as a 1000 ohm. So this is given to me. Now if you see here, this Vs, what is given to you, since Vs is given to me, the Vs is equal to, can I say what is the maximum value of this Vs? If I compare this Vm sine omega t, if I compare this with Vm sine omega t, so the maximum value of this is 200. So I can say that this is 200 volt. Now whatever derivation I have done is with respect to this Vi. Remember that this is my Vi. I am interested in this Vi. And suppose I say that this is point A, this is point B, and this is point C here. So what is the voltage between A, B? Will be step down version of this transformer. The voltage at the secondary of this transformer will be step down. So I can say that Vs upon VAB. VAB means voltage between A and B will be equal to the turns ratio N1 upon N2. So this implies that I can say Vs is given to you 200 upon VAB, means potential I find between points A and B, will be equal to N1 upon N2 is 5 upon 1. 5 upon 1. This implies that voltage VAB, voltage between point A and B, maximum value of course, will be equal to 200 upon 5. So it will be 5 4 is 40. 5 4 20, yes, it is 40 volt. Now this is the voltage 40 volt. I am interested in VI, maximum value of VI. So VI, or I can say that the maximum value of this VI, because this is maximum value. This is V, of course it will be 40 sine 50 pi t. If I say what is 40, it is 40 volt maximum. It is a maximum value because I have considered this as a maximum value, so it will be the maximum value automatically. Otherwise exact value is between this and this point is 40 sine 50 pi t. I am not writing it. So it is VI maximum. VI will be 40 by 2. 40 by 2. The point to be understood is this point only, that is the potential between this point and this point, maximum value. It is 200. So maximum value of between this and this will be 200 upon 5. It is 40. Now assuming that this is exactly center tapped, so it is equal to 40 upon 2, that is 20 volt maximum. This is equal to 20 volt. So this implies that I get this value now simply Vm is equal to 20 volt. Once I obtain this, rest everything is quite simple. Let's come to the first part of the problem. That is Im is equal to Vm upon Rf plus RL. Vm, you have found that this is equal to, simply substitute these values. This Vm is 20 volt, substitute this as 20, this Rf as 50, and this RL as 1000, and you will get this, whatever the, sorry, it is 20, not 0, 20. Alright, so this Im, I hope that this is clear to you. This implies that you will get the value of Im will be 20 upon 1050, this much ampere. Next, IDC is twice Im by pi. Second part, I am writing here only. IDC is equal to twice Im by pi. This is Im, so it is 40 upon this factor, this much ampere. Im you have already calculated, you substitute this value. IRMS, third part, no, it is first part only, not second part. First part has 3. IDC, IRMS. IRMS will be Im upon root 2. So IRMS you have calculated, this you have calculated. Now simply I am just giving the result here only. That is, you will find the value of PDC. Next part is to find the value of PDC. Okay, I'll use another page. The next part of the problem is to find the value of PDC. Now what is PDC? We have already done that. Value of PDC is equal to IDC square into RL. IDC, I have just calculated, IDC is equal to twice Im by pi. Twice Im by pi. So it is equal to twice Im by pi whole square into RL, and of course this will be twice of Im. Im is equal to this much, 20 upon 1050. So it will be 20 upon 1050, pi is already there, whole square into RL is 1000, this much watt. Kindly do the calculations. Similarly, PAC will be IRMS, it is equal to IRMS whole square into RF plus RL, this is the point here, into RF plus RL, and the value of IRMS is equal to Im upon root 2 whole square into RF plus RL. Again you substitute this value of Im is equal to this much, twice Im by pi, twice Im by pi. I have written only Im by pi, so this 2 is missing here, I'm sorry. It is twice Im by pi. IDC is equal to twice Im by pi, so I have to use twice Im by pi. Similarly you can find this Im, substitute the value of Im here, and it is equal to this much. So Im is equal to Vm upon Rf plus RL. Yes, Im is equal to this much. IDC is twice Im by pi, and it is equal to this much. So I hope that this PDC and PAC are clear to you. This much water. Simply substitute the value. And last part is to find the efficiency neta. Third part of the problem, or fourth part. This is second part. This is third part, and fourth part of the neta is equal to PDC upon PAC. Either you find by this, or you find neta is equal to 8 upon pi square into RL upon RF plus RL. You'll get the same result from both the sides. So I hope that this is clear to you. I'll stop it here. Thanks for the time being.